Welcome, everyone. Today, we are going to explore a massive leap forward in edge computing, the autonomous blueprint. We'll be looking at how we can achieve end-to-end large language model, or LLM, deployment on complex spatial NPUs using something called agent skill systems. Historically, mapping compute tiles and local memory pools on NPUs required intense manual engineering. But as you can see in this blueprint, we are introducing an automated pipeline where AI agents handle deployment, execution, and output analytics, guided by human-crafted skill systems. To understand why this matters, we have to look at the edge AI deployment bottleneck. Let's look at the status quo. While spatial NPUs offer incredible energy efficiency, unlocking that efficiency requires labor-intensive expert engineering, custom compilers, and manual optimization that can take weeks or months. It's a fragile process hampered by a severe skill shortage. But our breakthrough changes this completely. By moving from a human-guided copilot to a fully autonomous engine, we achieved self-learning, continuous adaptation pipelines. The result? We deployed 8 completely novel LLMs in just half an hour to 4 hours of agent wall time, with zero human coding required. The root of the deployment bottleneck lies in a fundamental architectural shift. When you write code for a standard CPU or GPU, the hardware manages your cache and data movement automatically behind the scenes. This is implicit management. However, spatial accelerators like the AMD XDNA 2 NPU rely on explicit management. Developers must manually control tile-level kernel placement, distributed on-chip memory, and exact data movement scheduling. This explicit control allows for great efficiency, but the coding complexity is immense. So, how did we build an AI that could handle this complexity? We started with stage 1, the human-guided copilot. We tasked AI agents, specifically Claude Code and Claude Opus 4.7, with deploying the BF16 Llama 3.2-1B model using MLIRR and iron tooling. At first, it was a messy, iterative process. We hit memory leaks, sync errors, and pipeline stalls requiring constant human debug loops and manual fixes. Because the error messages were opaque and the tooling documentation was sparse, every new debug session risked breaking past fixes without persistent memory. Through that grueling stage 1 process, we eventually developed a 3-pillar optimization framework. Pillar 1 is kernel efficiency, focusing on vectorization, shape-specific tuning, and fused kernel designs like flash attention. Pillar 2 targets dispatch overhead. By aggressively merging pre- and post-attention kernels, we drastically cut per-layer dispatches from 15 down to just 3. Finally, Pillar 3 is host-side optimization, which focuses on XRT context reuse and skipping redundant host device transfers through zero-copy buffer mapping. This optimization framework yielded incredible performance. We completely surpassed the hand-optimized iron baseline. Our prefill time to first token sped up by 2.2 times, dropping from 2.7 seconds down to 1.3 seconds. Even more impressively, our decode throughput achieved a 4.0x speedup, jumping to 10.8 tokens per second. It was clear the optimization trajectory worked, but it still relied heavily on manual human direction. Our next major challenge was clear: removing the human. To remove the human, we needed to codify all of that trial-and-error exploration into persistent memory, a process we call the synthesis. We took all the chaotic chat logs, opaque error messages, and profiling data and filtered them through a strict documentation discipline. The agents were forced to continuously write and update strategy plans, optimization logs, and bug root causes into markdown files. This synthesized knowledge became the foundation for reusable, composable agent skills. That synthesis led us directly to stage 2, the autonomous engine. This is our fully automated pipeline. It builds a CPU oracle, validates the kernels, verifies the single blocks, and checks the full model before moving on to prefill and decode optimizations. The brilliance of this engine is that if it hits a runtime failure, buffer corruption, or routing congestion, it triggers auto-invoked debug skills based on strict numerical gates. Finally, the deployment is handed off to an independent evaluator. Let's talk about those numerical gates, because they are how we secure correctness. Optimization is useless if the math is wrong. We use a phased approach, starting by decomposing a Hugging Face model into a pure CPU reference in phase 0. As we wire kernels together up to a full N-layer model in phase 3, the output must pass strict thresholds for absolute error, relative error, and Pearson correlation. If it doesn't pass the gate, it doesn't move forward. At the heart of the deployment agent are two continuous, automated loops, the debug loop and the optimization loop. The agent checks an issues log to diagnose hangs or corruption, and references an optimization trajectory to attempt multi-kernel merging or buffer reuse. Our strict system requirement is that optimization gates only pass if the new step measurably improves baseline performance while maintaining absolute numerical correctness. Because AI systems are notorious for finding ways to cheat metrics, we instituted Phase 7, the independent evaluator. Once the deploying agent finishes its work, the final deployment and profiling report is passed across a strict barrier of context isolation to a completely separate independent evaluator agent. This agent rebuilds the validation from scratch, reruns all numerical gates, and reprofiles the hardware to completely prevent any reward hacking. When you look at the evolution of NPU deployment modalities, the leap is staggering. The hand-optimized baseline required months of 100% manual work to deploy just a single, specific model. Our Stage 1 human-guided copilot brought that down to weeks for the Llama 3.2 model. But with the Stage 2 autonomous skill system, engineering time dropped to between 0.5 and 4 hours with near-zero human intervention. Most importantly, it achieved fully functional generalization across 8 previously unencountered LLMs. And here is the proof, our factory output. The autonomous system successfully deployed 8 unencountered architectures, including those with multi-head attention like SmallLM2, grouped query attention like the Qwen 2.5 series, and models with unique QKV bias or per-head normalization like the Qwen 3 family. These represent the first open-source end-to-end deployments on the AMD XDNA NPU, and all of them passed those strict numerical gates in just hours. To fairly evaluate how our system generalized across different model sizes, we created a metric called ADA scale. This normalizes the sustained hardware efficiency, measured in flops or bytes per second, against our Llama 3.2-1B reference deployment. By setting our reference model at exactly 1.0, we can accurately compare the decode and prefill efficiency of wildly different model sizes on an even playing field. When we analyze the scalability using ADA scale, we discover some powerful insights. Models like Llama 3.2-3B and Qwen 2.5-3B scored greater than 1.0. This is because their larger matrix operations naturally amortized the per-launch dispatch overheads much better than the reference model. However, the Qwen 3 family scored below 1.0. Our autonomous insight revealed that their smaller per-kernel workloads failed to amortize dispatch overheads, and their novel normalization operations weren't yet automatically fused by the system. Ultimately, what we have done here is redefine the hardware abstraction layer. Traditionally, rigid, narrow compiler stacks were the only layer sitting on top of resource-constrained spatial accelerators. We have injected a new layer, agentic skill systems. We are moving the industry from single-kernel optimizers to full end-to-end orchestration engines. The spatial NPU deployment bottleneck is no longer solved by months of grueling expert engineering. It is solved by distilling human knowledge into autonomous, scalable skills. Thank you for watching.